Hello, everyone, and welcome to The Vertical Space, a podcast at the intersection of technology and flight. We are your hosts, Jim Barry and Luka Tomjanovic, and here we look at the most important forces shaping the market of advanced air mobility, with a particular focus on why and how they matter to those building a business in this very exciting and growing industry.
You have to start with the mission and the customer. Who is the paying customer? How does this generate value? Who's paying for it and why? And how do we do this job today without drones or advanced air mobility? Because you're competing against the existing modes of transportation fundamentally.
Hey everybody, welcome back to The Vertical Space. You'll enjoy Professor Olivier de Weck's discussion on a lot of levels. From his new book, in fact, released the week of our podcast recording, Technology Roadmapping and Development, you'll hear how companies can focus their tech investments for optimal return. Professor de Weck is Professor of Aeronautics and Astronautics and Engineering Systems at MIT. So listen to his perspectives from academia and industry as an executive at Airbus on the importance and proper application of tech road mapping, on the limitations of batteries to today's and tomorrow's vehicles, and the value he places on hydrogen for advanced air mobility. Listen to his fresh opinions on what we can learn from nature and nature's best flyer and the importance of bio-inspired design. Enjoy how he describes that there is yet to be a dominant design in any area of advanced mobility, like the Model T to automobiles. Listen to his response to Luka's questions on how startups and today's young advanced air mobility companies can learn from tech road mapping, where he explains how startups can't afford to make a mistake. And here what he says are the three biggest challenges that advanced air mobility has to overcome to realize its full potential, including the challenges in air traffic management, which are exciting opportunities for our listeners in private enterprise, along with those listeners from ANSPs. This is one of those conversations where you uncover layers of value the more you listen to it, from the value of road mapping to the value and role of batteries, to the lessons to entrepreneurs, to the importance of understanding the history of technology to apply future technology in a meaningful, sustainable, and valuable way. And you'll get to hear what kinds of companies Professor de Weck would invest in. Finally, let's talk a little bit about his book, Tech Road Mapping and Development. As Professor de Weck outlines in his book, it's so darn important that tech road mapping be done right, that the value of tech be quantified, that each step of the process be measured, and to fully appreciate, understand, and communicate the value that the tech will eventually mean to a company's customers and to the value to the company itself in terms of revenue, profits, and enhancement of overall market value. But here's the bonus in reading Professor de Weck's book. Into this really important and valuable topic, he weaves such entertaining examples and case studies like in transportation, energy, communications, and medicine. You'll also enjoy reading about the history of technology, and he explains why understanding the history is so vital as we identify, deploy, and generate real value with future technology. So sit back and enjoy our discussion with Professor de Weck. And then, a week later, listen to it again and hear yet another layer of value as you innovate in the vertical space.
This episode of the Vertical Space podcast is brought to you by UAvionics. UAvionics is the leader in low size, weight, and power certified avionics for manned, unmanned, and advanced air mobility aircraft. Let UAvionics help you achieve your goals, whether that be type certification, airspace access, or beyond visual line of sight operations. UAvionics has certified and certifiable communications, navigation, and surveillance avionics for your aircraft. So head over to uavionics.com or Google it to see how you can start flying safer and move your platform forward into shared airspace.
So let me tell you a little bit about Professor Olivier de Weck. He is the Professor of Aeronautics and Astronautics and Engineering Systems at the Massachusetts Institute of Technology, MIT. He earned degrees in Industrial Engineering from ETH Zurich and Aerospace Systems from MIT, including his PhD, where he is Faculty Director of the Engineering Systems Laboratory and Bernard M. Gordon MIT Engineering Leadership Program. His main research is in systems engineering with a focus on how complex technological systems are designed and optimized and how they evolve over time. Important methodological contributions that his group has made to the modeling of complex systems in aerospace and other domains like water, energy, and transportation include time-expanded decision networks, generalized multi-commodity network flows, as well as software tools such as SpaceNet and HabNet. Professor de Weck is particularly interested in the principles underlying so-called life cycle properties that only become apparent once a system, product, or campaign has been fielded and operated for years, decades, or even centuries. These properties of systems include, amongst others, manufacturability, maintainability, reliability, robustness, reconfigurability, flexibility, and more recently, sustainability. At MIT, he teaches popular classes on related topics such as systems engineering, satellite engineering, multidisciplinary design optimization, and technology road mapping and development. Besides MIT, he holds visiting appointments at EPFL in Switzerland and Keio University in Japan. He has authored or co-authored over 400 publications for which he has been recognized with 12 Best Paper Awards since 2004. His award-winning book, Engineering Systems, Meeting Human Needs in a Complex Technological World, was the bestseller at the MIT Press in 2012, was recognized by the Association of American Publishers, and it was translated to Japanese. He is a fellow of NCOSE, an associate fellow of AIAA, and a senior member of IEEE. He served as editor-in-chief for the journal Systems Engineering from 2013 to 2018. He and his group worked with NASA's Office of Emerging Space to develop new commercial space technology roadmaps, and he is a former senior vice president of technology, planning, and road mapping at Airbus, where he was responsible for road mapping a $1 billion R&D portfolio for the world's largest aircraft manufacturer. His new book on technology road mapping and development was published by Springer Nature in July 22. His passion is to improve life on our planet Earth through research and education in systems engineering, while paving the way for humanity's future off-world settlements. Professor de Weck, welcome to the Vertical Space, and I know you know Luka Tomjanovich.
Thank you, Jim. Thank you, Luka. What an honor to be here with you.
Oh, likewise. The honor is ours. Thanks for being on the podcast.
This week, you just had your book come out on technology roadmap, and we're so excited to talk about it. It's a wonderful book, and I hope we get into the meat of it and how it applies to our listeners. But first, we ask all of our guests, is there anything that very few in the industry agree with you on?
Well, and that I think when you talk about the industry, we talk about advanced air mobility here. Well, maybe I'll make a controversial statement, which I think that lithium-ion based batteries are not the future. I know we're using them a lot in drones and airplanes, but I think we're getting close to their maximum potential. And in terms of energy density, in terms of cycles, I do not believe lithium-ion batteries are the long-term future for air mobility. And that I think some people will not agree with.
Can we peel that onion just a couple more layers and tell us perhaps about whether this applies across the board or certain segments of aviation and advanced air mobility, and what alternatives are you most excited about?
Yeah, so I think that for the really small drones, the lightweight vehicles that fly just a sensor payload, or they do inspection, they have short missions, maybe below an hour. I actually I bought a new DJI drone last year, and I've been using it and I love it. But it has a 15-minute mission life, right? Especially if you're flying in windy conditions. 15 minutes is not a lot of time. Plus, you have to keep extra reserve so that you get your drone back safely, right? And you don't ditch it in the water. And so I think if you look at the the energy density, just based on the chemistry of lithium-ion batteries, there's an upper limit, an asymptote that we will never exceed. And we're not there yet. We have more room to grow. There's nanotechnology enabled lithium-ion batteries and so forth. But the ceiling is very clear. It's dictated by chemistry. And I just believe that there will be other chemistries. For example, closed loop hydrogen fuel cells, regenerable fuel cells. There's other battery chemistries. There's supercaps, right? Supercapacitors, which are way below batteries today, but their rate of improvement is faster. And that's actually one thing I write about in my book is disruptive technologies, how a technology that seems way inferior today will eventually take over, potentially, because its rate of improvement and its the ceiling, the headroom that it has is so much more. And so supercaps, I think, should be watched closely.
So as you introduce this concept, Professor de Weck, of the current battery may not be the battery of the future. So as we look at drones and advanced air mobility companies, VTOL right now, you see what they're projecting for the next 5 to 10 years. Do you feel they're being reasonable in their projections based on battery capability today?
I think the realism, I mean, I think we have a lot of great battery companies out there that are innovating in the battery space. And we know, of course, big investments like in automotive. Automotive batteries are improving a lot. You know, the Tesla batteries are still kind of leading, but I think others are catching up, like BMW, for example, is making major investments. So I think that for automotive, the lithium ion batteries are going to have more potential. I think in air mobility, once you start scaling up the vehicles, don't forget that, you know, drag scales with surface area, frontal area, linearly. It scales with velocity, flight velocity, quadratically, and power scales with flight velocity to the third power. The scaling laws, as you're scaling up your air vehicles to do more ambitious missions, you know, carry people, carry the cargo, right? Carry more sensing payloads or comms payloads. As you scale up those air vehicles, everything works against you. All those scaling laws work against you. But the batteries, the weight of the batteries, the number of charge and discharge cycles they can sustain is kind of static. And so there's a crossover point where the size of the vehicle, the length of the mission no longer supports lithium ion batteries being the top choice.
And before I want to start talking about your book, before we do, what's your guess from a timeline perspective when you look at the capabilities that are being projected? When do you think that the current battery will be able to meet the missions of the vehicles that are being discussed?
I think it depends what kind of missions we're talking about. I think the market for advanced air mobility is mature enough today that we can actually start talking about subsegments of that market. Right. So drones for Earth imaging, you know, and we see them being used in inspections, real estate, making movies, and so forth. Absolutely, the batteries are there today. But you know, the 15 to 20-minute duration, we would love to be able to operate a drone for an hour or two without landing, right? Without swapping batteries. But I think we'll get there within this decade. And then you have sort of a medium market segment where the primary value of the air vehicle is carrying cargo. So this is package delivery, last mile logistics, things like that. I think we're okay there for short missions. You know, there are just a few kilometers, 10-minute missions. And then when you start carrying humans over relevant distances, meaning distances of tens of kilometers in larger metropolitan areas, that's where I think we won't get there, not even by 2040.
What do you think are some of the either unintended consequences or consequences that people tend to not pay attention to when it comes to energy that perhaps ripple through how the network is deployed, maintenance, you know, any downstream effects?
Yeah, I think it's a fantastic question. My short answer is you got to have a full life cycle perspective. So where do the metals come from? You know, nickel, all of the rare earth metals that go into the batteries, the anode, the cathode, the electrolyte, the housing, the membranes, where are those sourced from? Are those from primary materials? Are they from recycled materials? The battery assembly process, the deployment of the batteries, the charge discharge cycles, either onboard the vehicle or battery swapping. At what point do you take the battery out of commission? Like, is it when, you know, its depth of discharge or its capacity is down to 90%, 80%, 70%? What happens to the battery once its primary use is finished? Do you recycle it? Do you just dispose of it on a landfill? Do you resell the battery for a secondary application that's not a mobile application? You know, like for energy storage in homes or industrial applications.
Sure.
And so I think there's a whole ecosystem around batteries that's actually beyond just the starting stage, that's already maturing quite rapidly. And especially when we think about disposal and recycling cost, there's a lot of innovation that still needs to happen. I'm personally a big fan of salt batteries, like the Zebra batteries. We just had a thesis on that topic here at MIT, and they're really great for energy storage. And it's table salt and metals, you know, not rare earth metals. So extremely easy to recycle, no toxicity, no risk of fire. So the metal and salt batteries are very, very promising. but their energy densities are not that great, and so they may not be the first choice for air vehicles.
Tell us a little bit about, for the limited time that we have, and we have so many questions I'm sure our listeners are going to want to hear answers to. Tell us a little bit about technology road mapping and development. Your book, again, came out this week. Give us the highlights, if you may, and then what we want to be able to talk about is, given your background in industry, academia, the writing of the book, how it applies to advanced air mobility.
And I should say we are recording this on this 21st of July. So this is the week that the book is coming out.
2022.
2022, yes. Thank you for all of those time travelers.
Well, first of all, thanks for the opportunity that you're giving me to talk about it. The history of this book starts in 2016 when I had coffee with Paul Aramenko at the time. He was the founding CEO of A-Cubed, which still is a Silicon Valley-based innovation company that was started by Airbus, the very large aerospace company that many of you are familiar with. And at the time, Paul had been appointed as a chief technology officer for all of Airbus. And he was heading off to France, and he said, I need help. Airbus is a big company, 130,000 employees, spends about 3 billion euros per year on research and development, about 1 billion, so about 1/3 on what's known as R&T, so research and technology development. And it's a mess. There's hundreds of projects. We don't even know all the projects, how to group them. Are they really targeted toward the future ambitions and products and services? Or are they just pet projects, basically? So, I spent 2 full years. I took a leave from MIT. I spent 2 years in Toulouse in southern France, basically putting in place a team and also a method for organizing, preventing chaos in the research and development portfolio. And it was a tough time. It was a very interesting time. I'm very proud of what we achieved there. And part of my contract with Airbus was that I could write a book about it. And so I started writing the book when I got back in 2019, back to MIT. And initially I was thinking a kind of a narrow book, but the more I wrote about it, I started including other topics that I had researched before, like the history of technology, the relationship between technology and nature. And then the last chapter, which is almost science fiction. Where are we going to be in 50 years, in 100 years? And so it became much bigger than just, here's an approach to do road mapping.
I have to say, and Professor de Weck, I mentioned it before the podcast when we were just talking. I read it because I thought it was going to be important. Having read it, it was stimulating. I think people are going to love the history of technology. I think that the history of technology is going to be so important as we quantify the value of technology road mapping. And the case studies that you use throughout on automobiles, aircraft, deep space network, and DNA sequencing, I think it's an entirely readable book that I think people will really enjoy. And then also, if I may say, one of the problems today we have with R&D or R&T is we can't quantify its value to be able to, substantiate the investment. Reading a book like this and deploying its capabilities, maybe we'll spend a little bit less money on stock buybacks and spending more on technology to improve the real value of our companies. But I think this book will play a critical role. So forgive me for I can't hold back my enthusiasm. It was a great book.
We didn't prep this, so it was spontaneous, of course, and I really appreciate what you're saying. And one of the things that I guess since I'm a faculty member here at MIT, one thing that we're drilling our students on, like every day, every lecture, is quantification. Don't just talk in general terms, but always try to quantify what you're saying. And you mentioned the chapter on the history of technology. And there's a lot of technologies, the technologies that handle matter, right? Information, energy, and so forth. And it was really interesting. I call them figures of merit, right? FOMs, yes. Figures of merit. Yes. What is the figure of merit? And so a technology can advance rapidly in one figure of merit, but be kind of stalled out on another. And one of the most interesting, as I was writing about information technologies, like how do we store information and how do we transmit information? You go back literally to the stone tablets, right? and how the old Babylonians used to write, and how they stored information on clay tablets or stone tablets. And then we went to papyrus, right, with the Egyptians. And then we went to paper and printing. By the way, paper was invented by the Chinese. And you're like, why did we transition to these other modes? And then, optical discs, and now it's all cloud. Well, it's because, the number of characters per cubic meter, or how many characters of information can you carry per unit mass. It's we talk about energy density of batteries earlier. Well, this is the character density on a medium. Those are the reasons, because things became lighter, more mobile. It was easier to transmit more information while spending less energy carrying stone tablets, from one town to another.
Right.
What are some of the examples of historical technology evolution, maybe one or two technologies that you think are most relevant to apply to the future of aviation? Some of the lessons learned that entrepreneurs or executives or investors should be paying a lot of attention to.
Well, that's a great question. One of the examples of historical technologies, by the way, for my students here at MIT, I have an exercise where I ask them to pick a not necessarily prehistoric, but let's call it medieval technology before the year 1500, and describe it, model it, why was it important? So I talk about in chapter 2, I talk about the Portuguese caravela, which was a very specific sail ship. And what was specific about the caravela was that it was able to do coastal navigation well, around Africa. The Portuguese established their colonies. They broke the monopoly that Venice had, right, on trade, because they had these ships. And so sail ships, the history of sail ships, I think, is interesting to think about as we look at aviation, because the ships became more specialized. Warships looked different from trading ships. And then you had hybrid ships, and you had different categories of ships for different purposes. And that's what we're seeing in aviation is, regional airplanes versus cargo freighters, and so forth. So I think we have a lot to learn still from naval architecture, which is actually where aviation started. Like here at MIT, the aviation program started out of naval architecture. The other thing I would say, Luca, is I think we have a lot to learn still from nature. So I have in the book a picture of, it took me quite a while to hunt down the actual photographer who took this picture, but it's a picture of an albatross with its wings deployed. And he took this picture on an island in the Pacific, very remote. The albatross is just amazing as a glider. It's nature's best flyer. And it has a lift over drag ratio of 23, an aspect ratio of 15. And I learned some stunning things about the albatross. For example, when the albatross spreads its wings, in the shoulder joint, the bones in the shoulder, there's a locking mechanism. So the albatross locks its wings, and it can glide. It can do 1,000 kilometers a day, with the right winds. And it spends almost zero energy doing that, because once the wings are locked, it doesn't take muscle energy to keep them in place, which other birds don't have.
Unbelievable.
Yeah, it's amazing. It's amazing. And so bio-inspired, design has a long way to go still.
Right. I mean, even the way that birds navigate, and some of the birds that cross oceans, and even, almost the entire span of the globe, only to come back to the same tree from where they left, 10 months prior.
Yes. And honestly speaking, the more I wrote and the more I studied human-made, quote, artificial technologies, the more respect I have for nature. Over millions of years, nature has optimized. And what has nature optimized for? Well, efficiency, right? Minimal use of energy, minimal use of materials. So we have a lot to learn from nature.
Let me just quickly ask, and then Jim, I'll turn it over to you. But Professor, when you look at the drone space and this broad category of advanced air mobility, where are we now relative to the early years of aviation? Are we past the point of the DC-3 or the X-1 or some of the milestones that really defined the early years of aviation? Where are we now when it comes to advanced air mobility?
Maybe the closest timeline I could match it with is the automotive industry. The automobile was invented in the 1880s, for the Paris World's Fair. And I was actually just in Stuttgart last week visiting the Mercedes-Benz Museum, and they had a replica there of the Motorwagen 3, which has it's a single cylinder engine, quarter horsepower. and
You got to start somewhere.
yeah, they take kids on rides. It was really fun to see that. And then, the World's Fair, the one where the Eiffel Tower was built for in 1889. And then in the early years of the automotive industry, there was real competition between, there were all kinds of different vehicles with a front seat, the back seat, 3 wheels, 4 wheels, gasoline engine, electric cars, actually, right? In the early 20th century, steam engines. It was a free-for-all, basically. And I think it's in the the Ford Model T, for example, here in the US, standardization, that became what we call the dominant design, right? Once you start making hundreds of thousands of it or millions of it, and masses of people can afford it, it becomes the dominant design, and the other ones drop off. We are not there yet in this industry, advanced air mobility. So, but we're not at the very beginning either. So I think we're like in the 1910s. What happened in the automotive industry before World War One, where we had this very vigorous competition of ideas, prototypes, a lot of different companies jumping in. That's where we are. The dominant design has not yet emerged.
Given the book on technology road mapping, and again, based on your experience as well, what lessons from technology road mapping would you recommend to this group of entrepreneurs and people building businesses in advanced air mobility?
Wow, that's a good question. Let me maybe share 2 lessons that I think are useful. The first one is you have to start with the mission in mind, the mission and the customer. Who is the paying customer? How does this generate value? Who's paying for it and why? And how do we do this job today without drones or advanced air mobility? Because you're competing against the existing modes of transportation fundamentally. So are you competing on time? Are you competing on convenience? Are you competing on price? And that has to be very clear, like who's the customer, or there's different groups of customers. What are they valuing? How much is it worthwhile to save 1 minute of time instead of sitting in traffic? And actually, I did a little bit of modeling and simulation of urban air mobility with the eVTOL for different cities around the world. I did some of this work while I was still at Airbus, and it's really interesting to look at how much do people value 1 minute of their time saved, right? And it's very different. $1 per minute is a good number to start with. And would you be willing to spend $1 to save 1 minute of your time? Some people would, and many wouldn't. And the answer is different in different countries. So lesson 1, you have to start with the market in mind and then quantify those figures of merit we talked about: safety, convenience, mass, endurance, and then always connected with the financial value, not just the technical value. That, I think, is definitely the starting point. The second lesson is maybe about setting the right expectations with your customers, your investors. I think there's a lot of hype in the industry. There's a lot of over-promising. It's done out of, optimism, sometimes hubris, but I think I would invest in a company that is maybe more realistic, when it comes to timelines as well. Yeah, measured, realistic, always benchmarking against, the current state of the art. And so I would caution to be too optimistic. But that doesn't mean it's all doom and gloom and this industry doesn't actually have a future. I think this industry has a very bright future, but it's those companies that are really doing serious work and setting the right expectations that will succeed.
You mentioned doing road mapping at Airbus. Have you come across how startups do road mapping, and how important is that for startups?
Really great question. So there is, some people believe that road mapping is only useful for large multinational corporations, with billion-dollar R&D budgets. I don't think that's true. I think it might be even more important in a startup where you can't afford to make a mistake or too many mistakes. And you can only afford 2 or 3 prototypes before you run out of cash. So the level of performance of those prototypes, how much better or different they are than current products or services you're competing with. So yes, I do think, but a startup needs 1 good or 2 good technology roadmaps. It doesn't need 40 or 60 like we had at Airbus.
So when you think about the future of aviation and advanced air mobility, what technologies would you highlight? We talked about energy, but some other technologies that are relevant for the industry to mature. And if you can comment a little bit on the timelines for the maturation of this technology to become commercially viable.
The way I would go about answering this is I would take a functional approach. And so in the book, I also talk about there's a 3x3 and then the larger 5x5 matrix of how to group technologies or classify them. So what are the key functions that you need in an advanced air mobility system? First of all, you need to load the vehicle, right? So passengers, cargo, sensor payloads. So the configuring the vehicle for its mission is important. That's even before takeoff, right? Then you have taking off, you have flying either in uncontrolled or controlled airspace. That's very important. So there's guidance, navigation, control, there's propulsion, there is collision avoidance. The weather and the winds are critical. The smaller the vehicle, the more the dealing with wind is going to be important. There's the landing, there's the turnaround between flights. How quickly can you do that? How much manpower is involved in turning around your vehicles? That's going to be a big driver of economics. And then there's also the technologies that we need on the ground, right? So not just vehicle-centric technologies, but infrastructure technologies for UTM, right? Urban traffic management. It's a big topic. Both Europeans, the Asians, the US is investing in at least studies of urban traffic management and perhaps also some demonstrations. But we don't have a universal standards yet like we have in commercial aviation, large-scale commercial aviation. So let's not forget about those terrestrial infrastructure technologies. So a lot of those things exist in theory or exist in a prototypical fashion, but not yet as a standardized, robust infrastructure. And so, even though the air vehicles themselves are progressing rapidly, we're seeing really good progress on air vehicle development. The development of the supporting ground and guidance infrastructure is lagging, I would say.
And Sarah, you talk about in your book how that was an important part of the highway system, for example, of the proliferation of cars. You're right. Almost it appears so much of the investment dollar today is going into the vehicles, but there's so much that still has to be done with infrastructure.
That's very true. And if I can just chime in on this, and we have a chicken and egg problem, right? It's do you build the roads first and then the vehicles will follow, or the vehicles reach a critical number of them and then the drivers are asking for better roads? And I think it's definitely a chicken and egg situation. Really interesting, the history of highways. So in Germany, it was during the Weimar Republic that the Germans started an interstate system. In the US, of course, the interstate system, the Eisenhower system, which in the 1950s, those highway systems cost a lot of money, taxpayer money, and they were all sold as military projects. The main reason for political support for them is to say, we need to move our troops. If we have to shift our troops from one part of the country to the other quickly, we need reliable highways. And who can argue against that, no matter where you fall on the political spectrum? And so I'm not saying that that's the answer for advanced air mobility, but I think it's still true that a lot of these really expensive national infrastructures, if there's a way to show the benefit of them for national security, national defense, there's usually easier to build political support to build them and put those billions of dollars into it, rather than if it's just a purely commercial play.
You mentioned some of the technologies that are still maturing. Are there any that you're particularly excited about that deserve innovation and entrepreneurs putting forces and brains together around?
Yes, I'll mention a couple of them, and on the first one, I will show my Airbus bias here. So my apologies to those of you who don't agree with this statement, but I do believe that hydrogen has a future. And, hydrogen So this is hydrogen as the fuel of the future, certainly for air vehicles. And the reason for that is that we can produce clean hydrogen. Hydrogen has extremely good energy density on a per mass basis, not as good on a per volume basis, right? If it's gaseous or liquefied hydrogen. Nevertheless, if we can handle the safety issues, see, a lot of people still, the ghosts of the Hindenburg, right? It's time to move past the ghosts of the Hindenburg and see the full potential that hydrogen has as a universal fuel for cars, for air vehicles, even for producing electricity. And the reason for that is that, first of all, don't forget, hydrogen is the fuel of our sun. Our sun uses hydrogen as its fuel. Okay, it's fusion, but I'm just a big believer that over time, hydrogen will become more important as a source of fuel. And then the other is, if you're looking for efficiency in a flying thing, whether that's a drone, a small plane, fixed wing, the way that birds, look at the birds and how they fly. The Wright Flyer was bio-inspired. I mentioned bio-inspiration earlier. There's just so much efficiency to be had in fixed wing, but you could do fixed wing with deployable wings, with tilting wings, and we're seeing a lot of that in I think the community now. Once you're airborne, even at very low flight speeds, it's very difficult to beat the efficiency of fixed wing. I'm a big believer in smart, intelligent, bio-inspired mechanisms that eventually are fixed wing, but when you're taking off and landing, look at the birds.
Let's say it's 30 years from now, and I'm actually going to step on one of our closing questions here with my question. 30 years from now, when advanced air mobility has been wildly successful, what are some of the bigger challenges that will have been overcome to ensure its success?
Many challenges will have been overcome. So I'll mention two of them. One, I think we already talked about, which is air traffic management. The airspace today in most parts of the world is segmented, into Class B, Class C. In the US, unless you have a special license, you're supposed to stay below 400 feet. So we have this kind of somewhat artificial separation of the airspace into these different regions where different rules apply. I think we need to break that down. I think once you open up the third dimension, if you can manage that airspace more intelligently than we do today, there's a lot of room for everyone up there. So that's number one. Number two, it's about energy. How do you get the energy that you need to fly into those air vehicles? Where does the energy come from? How do you fuel or recharge those vehicles? How do you do it in a much more distributed way than is today? Today we have those big airports, right? And you have, look at LAX, for example. LAX sits right next to a major refinery. So the refinery is right there feeding all this Jet A fuel into the tanks, and then it goes into the airplanes. Not every airport or vertiport is going to have a refinery right next to it. So how do we get the energy generated, stored, and then onboard those vehicles? And that's where renewables, whether it's solar, wind, geothermal, hydrogen, locally produced hydrogen. That's what I'm talking about. So a distributed energy production and supply system, which can be used for a lot of other purposes, not just flying. And then the third big challenge is public acceptance, primarily because of safety concerns, not just of people in those vehicles, but also people on the ground. There's some reticence, I think, by the general public to accept, hundreds or thousands of air vehicles of very different kind flying, buzzing all around us. And the noise, of course, is an issue, but public acceptance may be the hardest of those to overcome. I think we can, and I think the rate at which it will happen will be different in different parts of the world.
Professor, as you were, again, looking at technology evolution throughout the history, did anything stand out in terms of the risk appetite and how that has changed over time? And what does that say about the adoption of new technology in flight, in the aviation domain?
I think it comes down, in the end, my read on what technologies have been successful or where people actually invest in making them better, which ones fall by the wayside and get retired. It always comes down, and for really centuries or even millennia, it's come down to economics. It's look at a really cool part of the history of technology is James Watt. People think James Watt invented the steam engine. He didn't. Newcomen invented the. Newcomen is the one who sold the first commercial steam engine in England. What Watt did was perfect the steam engine by introducing the condenser and making it much more efficient, having a cold sink basically. And what he also did, and that's why when we talk about power, we talk about watts. So he deserves he deserves to have his own unit of measurement. He did experiments with horses, pulling up water and rocks with horses, and then doing the same job with his steam engine to compare them side by side and demonstrating to mine owners, for example, that they were better off buying one of his steam engines than keeping a stable of 30 or 40 horses who all need to be fed, who all need to sleep, to pull up the water out of the mine. And so the economics of it is crucial.
You're suggesting that the value and the economics of a new technology will overcome the friction imposed by the risk aversion and the fear of introducing something that is not proven and not yet safe enough.
Yes, I think that's right. And you could almost flip it. I would say this way: only those technologies that can economically outcompete the existing solutions will eventually thrive and survive. I was thinking a lot about the Supreme Court here in the United States, the Supreme Court decision from a couple of weeks ago about the EPA, kind of limiting the EPA's ability to regulate, in terms of decarbonization and so forth. Mm-hmm. And, a lot of people are upset about it. The way I think of it is, if you have to, for over decades, regulate and prevent certain technologies from being used, or you're through regulation forcing the adoption of new technologies, but economically it doesn't make sense, you will always have resistance. And so I think those clean technologies we talk about, which we also are interested in advanced air mobility, of course, they're just going to have to come to the point where it's cheaper to do an AAM solution than a traditional land-based solution. Mm-hmm. When you include all the economics, the time lost, the hassle of ground transport, congestion, everything included, doing a 6-minute flight to deliver a package over, in a rural area versus a 90-minute drive with a small truck to deliver that package. Once it becomes economically more attractive to do it with a 6-minute flight and drone, regardless of regulations, et cetera, then people will start adopting it naturally.
So you have an audience of well-financed and extraordinarily talented CEOs and their heads of R&D. And they understand that they have to, as you talk in your book, understand where are we today, where could we go, where should we go, and where are we going? If they said, what investment should we innovate on to be able to have the greatest impact on our transportation system and on the returns on investments to our companies, what would they be?
You have to start with mission concepts, the ConOps, concept of operation. Who are your customers? What are your missions? With current technology, whether it's somebody else's vehicle or technology or your own prototypes, how well can you execute that mission today? If your vehicle or a solution didn't exist, how would that mission happen, or would it happen? And how good do you have to be, quantifiably good, to beat the current best way of doing it? And if you can't answer that question either through a demonstration or a model or a simulation that has some credibility in it, then I don't think you'll be successful. But if you can, then people will listen to you, customers, investors, and then of course you have to follow through on it.
Good point. Very relevant to the book. If you fast forward 5 years and then 10 years, what does advanced air mobility look like?
Depends where in the world, but I think we're going to have, in 5 years, we're going to have a proliferation of drones in everyday life, in logistics, in Earth observation, in police work, archaeology, you name it. I mean, I think the most successful drone companies in the world are seeing double-digit growth, right, in terms of sales of their products. But we're not going to see a mixing of air traffic of different kind just yet. I think a decade or two from now, in some, and let's call them enlightened countries or regions of the world, Places like New Zealand come to mind. They're pretty open-minded, I think, in terms of new technology. We're going to see a really exciting mix of traditional and new AAM solutions coexist. But I think it's especially in the really high density areas like US, LA, New York, Europe, Paris, London, etc. And then Tokyo, it's going to be harder. China, Beijing, Shanghai, it's going to be harder to have this mixing of air traffic. I'm personally very excited about the 2024 Olympics in Paris, where it's been announced that there will be an urban air mobility service that will be offered.
Professor de Weck, given we only have a minute left, if you were just going to leave one point with our listeners, what would it be?
If you want to create the future, understand the history of technology. They both go hand in hand.
Professor de Weck, you've been terrific. Luke, anything else from you?
No, thank you very much. This was a really, really fascinating conversation, and thank you for being the guest.
Jim, Luca, thank you, and thanks to your listeners, and go innovate.
All right, that's a wrap for today. Thank you for listening to the Vertical Space Podcast. Reach out if there are topics that you would like us to discuss, and goodbye until the next episode. Unless mentioned, this podcast is in no way endorsing or promoting any person and/or company mentioned, and all opinions within the podcast are solely that of the presenters. The Vertical Space makes no guarantees, warranty, or representation of any information given in this podcast. Any information given is for informational purposes and should be used at your own risk. This podcast is for general, educational, and entertainment purposes only.